Okay, so let's start again. Okay, so yeah, so we finished with the adders, and then let's continue with our next topic, which is multipliers. Now, after adders, we are going to go for multipliers and then dividers, and then we are going to go for the floating point addition, subtraction, and multiplications. Okay, so adders can do both addition and subtraction. As we said that it's just a simple 1 and 0 at the carry input. So if you have and that's the good thing about two's complementary number system, that if you want to add two number, the same circuit can do also the subtraction, right? So we discussed about that in the last class. Okay, so let's go for the multiplication. So what is multiplication? So so you have done all this thing earlier as well, but we are now talking about with respect to computer arithmetic, right? So computer arithmetic is a little different than a normal arithmetic. So in multiplication, we have three things here. We have a multiplicand, which we denote as a multiplier, which we denote as x, and we have a product, which is actually a multiplied by x, right? Now, what's the difference in computer arithmetic? So in computer arithmetic, what happens is if you have got k bits for multiplicand, then you would consider k bit for multiplier, and the product would be of 2k bits, right? Because if you multiply 2k bit numbers, the maximum you can get is a 2k bit number, right? So this means that whenever you're going to multiply two numbers, you are going to get the proper results. So it's not going to be anything missing from that result. It's going to be the complete result. So that's why we have a product of uh, 2k bits. Now, if for any reason we have a multiplicand of more bits than the multiplier, then the product is obviously the sum of the bits of multiplicand and multiplier, right? So this is simple here. So if we have, say, for example, if we have k bits and k bits, so it would be k bit of multiplicand and k bit of multiplier. So the result would come in 2k bits. So okay, so I'll write it in a different way, not multiplier. So if we have got k bit for multiplicand and k bit for multiplier, then the result would be in 2k bits. Now if you have got k plus, or let's say not k, if you have got m bits for multiplicand and n bits for multiplier, then the result is going to come in m plus n bits. This is a general rule here, right? So if you have got m bits and n bits, the result should be of m plus n bit. But to keep it simple and to keep it regular, now regularity is an important property here when you are going to design anything. So regularity means that if you have selected the number, all of the registers should match that number, or a multiple of that number. So it can't be that you have a different number of bits for multiplicand and different number of bits for multiplier. That's going to complicate the whole design. So if a number is selected like k, then the same number would be selected for the multiplier, and the result would be twice that size. That thing makes things simpler, right? So what we are discussing about here is in multipliers, we have the product as number which is going to be uh, k plus k, right, or 2k. And this is how you have done multiplication whenever you have done it on paper. So a is a multiplicand, x is a multiplier. So what we do is, since it's binary number system, so each dot here represents a 0 or a 1. So what we have here is x naught, x1, x2, and x3. So we multiply x naught with all of these, and x1 with all of these, and x2 with all of these, and x3 with all of these, right? So this is what we do. Okay, so when we are multiplying two numbers, like 73 multiplied by, say, 28, right? So what we do over here is multiply 8 with 3 and 8 with 7, okay? And then 2 with 3 and 2 with 7. So actually it's not 2. It's not 2 that you're multiplying with, because we're talking about base 10 right now. So in whatever base you are, if that number is written in a particular base, then every digit is represented by the power of that base. So actually what you are doing is 73 multiplied by 8. So what you have done is broken this number into 20 plus 8. So this is what you know already. So what we do is 73 into 8 plus 73 into 20. So this is how we do it. Okay. So 73 into 8 plus 73 into 20, that's going to give you, because 28 is 20 plus 8, and then you're going to get the same answer. Now, the good thing about this thing, 73 into 20, is you can reduce this into just 73 into 2 into 10. Now this last thing here into 10, because it's base 10 and you are multiplying with 10, this thing can be replaced by another operation which is called as shift. So if you are going to shift any number to the left once and add a 0 to it, it is as if you have multiplied by 10. And if you do it once more, it is as if you have multiplied by 10 again, right? So if you are going to shift any number to the left, it is as if you have multiplied so by 10. So what we can do is we can avoid this multiplication by 20 by converting that into a number like 2, and then just simple shift it, right? And this is also going to work if you have a bigger number, like for example, you want to multiply 745 by 484, whatever. So again, the same thing here, that 484, your multiplier is 400 plus 80 plus 4. And this is how you do it as well when you're going to multiply it. So each time we are going to shift it, so 4 multiplied by 745, whatever the result is going to come over here. But that if you're going to multiply with 80, what you're going to do is put a cross over here or a zero over here and get your result of 8 multiplied by that number over here. When you multiply by 400, it's same as 4. So you put two crosses over here or two zeros over here and get your result over here. And then finally you're going to add all of them, right? This is how it's done. So what we are doing is we are trying to break that number, the multiplier, into different bits, and each bit is representing a different power of that base. So you can replace that by multiplying it by shifting it to the left, right? So this is easier way to do it. So we are talking about individual bits now, x0 and x1 and x2 and x3, and that is the power of that bit, which is basically shown here as shifted. So we are going to get different partial products. So if there are 4 bits, you are going to get 4 partial products, and in the end what you need is a result which should come as an addition operation at the end. So you have to get add 4 numbers, and then you're going to get the result. So this is simple multiplication. So if you want to convert this operation into an operation that can be understood by computer, so you can see here that there are some repeated steps, but you need to define those steps first of all, and then you want to do that. So what are those steps going to be? So what you can do is you can say, okay, I need to my multiplier, I'm going to break that multiplier into different bits, right? I'm going to start with x0, the first bit, multiply that bit with the whole thing. Now, if you're working in binary system, things get easier because you either have a 0 or a 1. So this would mean that you are either going to get the whole multiplicand, or you're going to get 0, right? So it's either going to be a or 0 at all these partial products, right? It's either going to be an a or a shifted a or 0, right? So this gets easier, but this is how we can translate it into an algorithm, right? Okay, so let's see. So we have got a right shift algorithm for multiplication. I'm going to discuss about the algorithm first, and then we are going to come to the hardware circuit for that implementation. We have got two numbers again, a and x. A is the multiplicand and x is the multiplier. So let's try to solve this, how to do multiplication. So we select a partial product, the product here, P register, as we know that it's twice the size of A and X. So we have selected it over here, right? So this is our partial product, the initial one. So we initialize it with 0. This is our first step. So we make that register 0, right? Then if our first bit is 1, we are going to copy A. If the bit is 0, we are going to copy 0. Okay, so there are two options, either A or 0. So since this is 1, we are going to copy A 1 0 1 0, and then we are going to add that. So 0 plus 0 is 0, 1 plus 0, 0 plus 1 is 1, and 0 plus 0 is 0, and 0 plus 1 is 1. And then we have another bit over here just to represent what should be shifted into when we are going to shift it to the right. So this is the right shift algorithm. We are going to shift the numbers to the right. Right? So this 0 is just to show what should be shifted at this point. Okay. Now remember, we are initially talking about unsigned numbers. So both of these numbers are positive numbers, right? So both of them are positive unsigned numbers. So okay. So this is the first step. These three are the first step, and then we have a next step, which is to shift that number to right once. Then go for the next bit. If it's 1, again copy that number, the multiplicand, add these two together, and then get some result, shift it to the right once more. So you're going to see we have 4 additions here. So one addition is over here, another is happening over here, The third bit is 0, so we are going to copy 0 over here, and still we are going to add and get the same thing, and then we are going to shift over here. That's the third addition. And for the fourth bit, that's the fourth addition, where we are going to have again 1010 added to it, with 4 additions and 4 shifts. So first shift happened over here, second over here, third over here, and the fourth over here. With 4 addition and 4 shifts, you're going to get a result. So let's see whether we have obtained the right result or not. Okay, so this is a 2's complement unsigned number. So let's see what our numbers were. So 1010 in unsigned number 10, right? Yes or not? What is the second number? 1011. Anyone?
It's 11.
11. Good. So
11.
so we are multiplying 10 with 11. Just you know what the answer should be. It's 100 110. It's going to be 110. So let's see whether we have obtained the right answer or not. So we have one at 2, one at 4, one at 8 position, one at 32's position, and 64. So what we need to do is add 64 plus 32. That would be 96. Plus 14. So 96 plus 14 is 110. So we have obtained the right answer, right? So you can do it yourself as well if you want. Right, so we have 10 into 11, which should be 110, and what we obtained is also 110. 64 plus 32 plus 8 plus 4 plus 2. So that's right answer. Okay, so that's not nothing difficult over here. It's easy. Whenever there is a 1, you copy the multiplicand, and at each step you just shift the number. Now when what's happening is when you're shifting that number, that bit is getting confirmed as part of your final answer. So 0 0 1 1, a 1 in the here, 1 over here, right? So that's the final answer, and each level you're confirming 1 bit. So that's the right shuffle algorithm. And this is how normally we also do that. This is normally how we do in base 10 as well. The method that we have learned to do multiplication. So if you are trying to do multiplication, as I've mentioned over here, so what we do is multiply the starting from the least significant digit or bit, and then moving on to the most significant, right? So it's here what we are doing is shifting it left, but what's happening is in the algorithm is that we are doing a right shift, but in other words, what's happening is we are focusing on this part that has to be added together, and we are doing an addition of these two at each step, right? So you're going to get this thing clear if you go for the next algorithm. So we are going to do that in another way. We are going to do the same multiplication through a left shift algorithm. That's the algorithm that can also do multiplication. In this case, we are going to shift our numbers to the left. Okay. The difference here is we are not going to start from the least significant digit or bit. We're going to start from the most significant bit, right? And instead of adding first, we are going to shift and then add. Okay, so it doesn't matter you shift or add or shift. So and it also doesn't matter if you go for the least significant first, the most significant first. So let's try to see how left shift algorithm is going to work. So again, the same number here, 1010 with 1011. Initially, we are going to start with a product of 0, right? And here the first step would be to shift left, not to add, but to shift left. So we are going to shift left first, the thing which is currently in P, and then we are going to look at our most significant bit first. So we are going to start from the most significant bit side. So if this is 1, then you're going to copy 1010 over here, and then you're going to add. So again, the same operation, addition, is going to be performed here, and you're going to get 01010. Again, the next step, shift left. The next bit is 0, so you're going to have a 0 over here. Add, you're going to get the same answer. Shift left, the next bit is 1, so you're going to have 1010 over here, add 01001, shift left, that's the fourth time we are shifting, and then the last digit is 1 over here, so 1010, and then add. So finally we got the same answer. Okay, so finally we got the same answer. We have 0 which was 110, and here also we are getting the same answer, 110. Now if I ask you to tell me which of them is better, what would your answer be? If I ask you in terms of computation time, or in terms of anything that you can state, uh, do you think right shift algorithm is better than left shift algorithm, or left shift algorithm is better than right shift algorithm, or both are same? Yes, I need your comments.
Hello?
Yeah.
Sir, maybe the right shift algorithm is faster because in first operation there is only adding. In left shift there is a shift then add.
Okay, so the operations that we have are shift and adds, right? So we say that an algorithm is better than another algorithm if there are fewer shifts or fewer adds, right? In that case, we could say that this is better. What we see here is we have 1, 2, 3, 4 additions and 4 shifts. So we have one shift over here, another over here, another over here, another over here. And if you look over here, again, there are 4 shifts, 1, 2, 3, 4 shifts, and 4 addition, 1, 2, 3, 4 addition. So in terms of addition and shifting, these two are same. So yes, anyone, are they equal? Or what can you see from this? Do they look equal?
So regarding the steps, you have said that the addition and shifting, they are the same, but I think the right shift algorithm is taking a cycle more.
Um, what is that cycle? I think so. They are taking the same cycle, because if I see here, this would be considered as our first step from here to here, right? So this is one step over here where you're going to add and shift. So okay, I'll say over here till here. So this would be one step over here. Then when you are going to add and shift, this would be a second step over here. And then when you're going to add and shift, this would be the third step over here. And then when you're going to add and shift, this would be the fourth step over here. So it's taking 4 steps because it's a 4-bit number. If you
Sir, but
want for, yeah.
the right shift, what is the benefit of the last shift operation?
So that's part of the operation. You are going to add and then shift. So this is the fourth and last shift. So this is going to give you the final result, right? Because what we if you're going to come to the hardware part, you're going to see we have got 8 bits for product here. So these are the 4 bits over here, and this is the extra bit that we have shown, as I've mentioned, that it's going to just tell you what's going to come on this side. So you can just imagine that this bit is not there, right? So what you have obtained at this point is a 7-bit number, right? It's a 7-bit number. So you finally have to shift it to make it an 8-bit number, and this is going to be your final answer. So as part of right shift algorithm, this last shift is important because our number is like this, and this is the something else, right? If you're going to shift it, then it becomes this 110. Otherwise, it's a bigger number than 110. It's twice of that. It's 220 over here, because we know that if it's not shifted, it's going to be twice of that number. So if you're going to shift it, then you're going to get the right answer in 8 bits. Okay. As part of left shift algorithm, we do a left shift first and then add. So this is going to be our first step till this point, and this is going to be our next step till this point, and this is going to be our next step till this point, and this is going to be our final step. So again, 4 steps over here. So there is nothing like one more step here in right shift algorithm. Anyone else?
Sir, is there a difference between the shifting phenomena? Since the steps they are taking are same, so it might be the difference between the shift. Left shift, I think, takes less time to get computed other than the right shift. So this might be the ground to compare them both.
Okay, so when we are talking about shifts, we are shifting into a an 8-bit register, right? So 8-bit register means there are going to be eight shiftings, 8 bits, which are going to change positions, and in a left shift there are going to still be 8 positions where there would be shifting. So again, 8 bits or to 8 bits, that's not a problem. So both of them taking 8 bits to shift their numbers either to the right or to the left, and so that's not a problem. But there is something here that you are missing. You people are missing over here. I need your answer because I always ask this question for my students and I wait for their answer. There is something going on which you people are missing. Okay. Let me just give you a hint. Right shift algorithm is better.
Say because it's incorporating less bits during computation.
How can you say that?
So because in left shift algorithm we are shifting first, so 0 bit gets added first and then it is being added in the next step. But in right shift algorithm we are adding first and then we are shifting, so the number of bits being used is less.
Your answer is correct, but your reason is not correct. Your answer is correct. Okay, so let's just come to that. Yes, your answer is correct. There is a difference in the adder. Now, if you consider over here, the adder is of 4 bits. The adder is of 4 bits at any position. But if you consider over here, that adder is actually an 8-bit adder. Because as you are shifting, as you are adding, you are not only adding the 4 bits, you are adding into the next bits here, and this is shown over here as well. If you're going to add these two numbers, where is that? Yeah, let's take this example over here. Now, what's happening over here is we had a number 0 1 0 1 0 0 0 1 0 1 0, and then you're going to add them. So it's not simple that you are adding these 4 numbers. If you are going to add these 4 numbers, you're going to get 0 and a 1 and a 0 and a 0, and then there is a carry. So where is that carry going to go? That's going to go over here. And so it's changed to from 0 1 0 to 0 1 1. Had there been a 1 already over here at this position, that carry would have made it to 0, and then there would be another carry over here. So the only difference in these two approaches is their adder. Here what's happening is in a right shift algorithm, we are finalizing 1 bit, which is the least significant bit in each step, as I've mentioned, right? And that bit is not going to change once it has been finalized in every step. Okay, here we could not finalize any bit because in the first bit we have shifted 0. Okay, luckily that is there in the final answer. In the second bit we have 1 over here, that is still over here. In the third we have 0, but that is not over here as 0, so that thing changed. This is just one example, but there could be changes even in this bit, the first bit that you have here. So actually what's not shown over, it's actually shown over here, but it's not visible, that this adder is actually an 8-bit adder. Because in a left shift algorithm, you have to add all of these bits together because the result has to be changed from that side as well. It could change the most significant digits as well. That's why when you're talking about adding, you start from the left hand side. You start from MSB side, not the left hand side. You start from the MSB side when you're going to add two numbers together, because you know that their effect is going to propagate it to the next levels and the higher levels, and then the higher levels are going to change. But if you start from the higher level, you are going to keep on changing themselves. So this is the problem with left shift algorithm. It starts from the higher level. So if I just illustrate it using this example over here, so what we are doing is starting with this side 4. So initially we are going to multiply 4 with 400 with 745. Now 400 with 745 is going to give us some number, right? And then we are going to add 80 into 485, and that's going to change that number without any result coming. So what we are going to do is, can somebody give me an answer of what is 4 into 745 quickly, so that okay, let me just do it myself. So 7 into
Sir, it's 2980.
okay, 2980. So 2980. Okay, so and 8 into 475, it would be 5960, double of that. Okay, this means okay. Okay, so if you're going to add these two together, you're going to see that the first result was 2980. But if you're going to add these two together, you're going to see that none of these bits are going to remain the same. So you are getting a different answer over here. So what you get is 35760. So none of these 298 has been preserved, right? Now if I do it like this, 2980, which was 4 multiplied by 785, and I add 5960 to it, so I would know that this 0 is my part of my final answer. So I don't have to take that into consideration. I just need to add these together. And once this has been added, I know that this result is part of my final answer. And whatever result comes over here, I just have to add 2980 to it to get my answer. So I'm not concerned with the remaining bits over here in this case, right? So this is the difference over here. In a right shift algorithm, you need a smaller adder. You can work with the smaller adder, right? So is this clear?
Yes, I
Okay.
got your point.
Okay, so let's move on. Okay, so if we do program multiplication, then here's a program shown over here. You can go through that yourself. But the main point of this slide is there are repeated shiftings and addition operations being performed over here. Sometimes you are going to skip the add if it's a 0. Now, if you look at this program, there are some initializations happening over here regarding taking that number from memory into some register. This is our main loop where it's doing the multiplication, then it's finally storing something over here. The problem with this is if you have got k bits, so they are going to be k iterations of the main loop because it's going to run k times, and this main loop is either taking 6 instructions or taking 7 instructions. So if it's a 0, it's skipping the add, only 1 instruction. So it's between 6 and 7, right? Which you can on average say 6.5 or anything. So it's and then there are few instructions for loading that into some register and storing that into some register. So those are 7 instructions. So it's either 6k plus 7 to 7k plus 7. So if you take an average, that would be 6.5k plus 7 instructions. Now if your k is 32, that number comes out to be 200 plus instructions. So you need 200 plus instructions for multiplying two 32-bit numbers. That's a huge number of instructions, right? So this means that you have to fetch 200 instructions, you have to execute 200 instructions, and decode 200 instructions. So it's a complicated process. So this means program multiplication is too slow and it's not feasible. So that's why whenever you're going to see higher, better computers, you're always going to see they have dedicated multipliers. for multiplication. These are the hardware multipliers. So program multiplication is not an option because it's too complicated. It's taking a lot of time. Okay, if you want to do it on 8086 for an 8-bit multiplication, I've written a small code for that. You can try it yourself as well, or you can make your own code. That doesn't matter. Okay, so the main thing here that I want to focus is we cannot go for program multiplication, so we have to go for hardware multiplication. So the same algorithm that we saw, the right shift algorithm, could be implemented in a programmed way, as we have seen, but it's going to take a lot of instructions to execute. So we need a better way to for a multiplier. So here in this diagram, we see our first hardware multiplier. And that's the same concept that we have discussed in that algorithm implemented in a hardware circuit, right? So initially, let's start with registers first. So we need 3 registers. In fact, there are 4. So 1 k-bit register for multiplier, 1 k-bit register for multiplicand, and 2 k-bit registers for storing the partial product. So k-bit over here and k-bit over. So these 2 registers are combinedly going to give us a result. So if we go for regularity, we go for k-bits. So we have got k, 2k, and k. So if you talk about number of k-bit registers, there are 4 k-bit registers. Actually, there are 3 registers: one holding multiplier, one holding product, one holding multiplicand. But this one holding product is twice the size. Okay, so again, this is a sequential circuit because working on a clock here, and there are registers which are loading here, so memory element is involved. Okay, so single bit is going to be shifted from the multiplier side, and we have a multiplexer over here, okay, which has an input of A or 0. So as I said, that it's easier for binary numbers because either you're going to add A to it or you're going to add 0 to it. Okay, so we have both these options in a multiplexer. So if the bit is 1, it's going to select the multiplicand. If the bit is 0, it's going to select 0. That's very simple, right? And what we are adding it with is the shifted version. We have designed the right shift algorithm, remember. So we are going to shift it right, and each time a bit, at every step, a single bit is going to be finalized, and that bit eventually is going to come to its right position after k number of steps, right? So and the one which is left over here at this side is actually the number that we were adding at each step. So that number is added with either the multiplicand or 0, and that is going to go on. And this carry out is going to determine the shifted input. That's once you're going to shift, that bit is going to remain empty, and that carry out is going to occupy that space. So it's a very simple diagram of a basic hardware multiplier, right? So the same algorithm that we designed could be implemented using a hardware multiplier. And this is going to be very fast because obviously it's going to take cycles, but depending on the delays of these adders and shifting operations, it's obviously much faster than fetching it from memory and decoding it and then executing it. So it's much faster operation. It's going to take 32 cycles. If your k value is 32, it's going to take just 32 cycles to implement a 32-bit multiplication instead of 200 plus instruction, where every instruction is going to take many cycles, right? So this is the simpler way to do multiplication. But remember, this was only for unsigned numbers. So let's talk about now signed numbers. Are there any questions here up till now?
No, sir.
Okay, so let's quickly go to signed multiplication. Now, looking at the same algorithm, the right shift algorithm, we are going to go on with that algorithm. Can that algorithm be used to multiply 2 signed numbers, right? So we try to do that first of all with that same right shift algorithm that we have studied. Then we are going to go to another scheme, the Booth's algorithm. So let's try to do it with the same scheme. So now we go with the first case where our multiplicand can be negative or positive, but our multiplier is always positive, right? So if the multiplicand is negative, but our multiplier is always positive, then what we have to do is we go on with the same step that we were doing in the previous slide. There is no change except that we have to look for the proper shifting. instead of doing just a simple right shift, we are going to do now an arithmetic shift. So what's an arithmetic shift? So maybe you people know it. An arithmetic shift preserves the sign. So if we have got two numbers here, 101, and we need to shift it to the left. Arithmetic shifts works right. Sorry, arithmetic shifts work when you're going to shift it to right. So normally this number is 5, right? So this is when you're talking about unsigned numbers, it's 5. But when you're talking about 101 to be a signed number, that's is not 5, because in signed numbers we treat this number, the first bit, as the sign the weight having a negative weight, the bit having a negative weight. So if it's a
Minus
1,
3.
if it's a 1, it would be considered as -4, right? So -4 plus 3 is going to give us -3. So in sign bit, this number is -3. Okay. Now, if you're going to shift it to the right, it is as if you have divided by 2, right? Now, if I'm going to divide it by 2, then I should get a negative answer. Okay. Now, if I'm going to shift it right, I'm going to get 1 at this point, the 0 at this point, and okay, so I don't have much space. So if I'm going to go to 3 bits, that this 1 is going to shift it out, and there is no space to hold it. But what should come over here? So what should come over here? That's the question. So what should come over here? So in a normal arithmetic shift, a right shift, this is going to be replaced with a 0. This is going to be replaced with a 0.
Okay, keep the sign.
Yeah, but in arithmetic shift, we keep the sign, because what's happening is when you are going to shift it, this negative number becomes a positive number. So that never happens when you divide it by 2, right? So in arithmetic shift, what will happen is if you have 101 and you want to shift it to the left, this number, the sign bit, goes to both these two positions, right? So it's the sign bit. It's not actually a sign bit, it's the MSB. The MSB is shifted to the right, and the MSB also comes to that same MSB position, right? So what is this new number? It's actually -4 plus 2 minus 2. So at least the sign has been preserved. So 3 divided by 2, sorry, -3 divided by 2 should have given you -1.5, but since you don't have any fractional part that could be stored, so that answer has been changed to -2, which is actually -3 divided by 2 if you can hold it only in 2 bits, right? So this answer is correct, and you can prove it with if you have got more bits. So if you have got more bits, then this number is actually -8 plus 2. That would be -8 plus 2 would be -6. -8 plus 2 would be -6, and -6 divided by 2 should give you 3, -3, sorry, right? Which in this case is going to happen because now it's -8 plus 5 or -3. So now you can see that you have obtained the right answer. That previous answer was also right, considering we just have 2 bits in this case, right? So this is arithmetic shift. So when you're talking about sign numbers, you're always going to go for arithmetic shifts, right? Always remember that. So since we are doing sign multiplication, right shift algorithm, so and now there are 5 bits. So the bits, the number of bits that you have in multiplier and multiplicand, actually the multiplier, the number of steps, the same number of steps you have to take. So if there are 5 bits, you have got to take 5 steps. So you're not going to stop after 4 steps. You're going to take 5 steps. Again, the same thing. We are going to start with the LSB 1 over here. Initially, our first step would be to take the partial product as 0. This extra bit here, the 6th bit. Now you can ignore that if you are quite experienced. But as a beginner, I would say that you keep this extra bit here, because this is going to help you in determining what should be shifted into that number, right? So this is an extra bit, uh, which is just representing the sign of that number, right? So during the computation or addition process, if you get a carry out of this, you just have to ignore that, because that's why you are taking that extra bit. So any carries out of that are not going to be considered. Okay, let's start. So this is one. So we are going to have a 10110. So we have written 10110. Now, this one is actually a sign extension of that. So if you have got a negative number, you are going to extend it by having another 1 over here as its sign. If you have a 0 over here, you are going to extend the sign. So if you're going to store a number in a bigger space, you just extend that sign. So everyone here knows that. I think it's known to all of you. So this number in sign bit is what? What is that number? Minus 4 plus 2, minus 2. And what is this number? Yes. What is this number? Anyone?
So
Kuchi?
minus 2.
Minus 2. This is also minus 2. Okay, so what is this number?
Okay, 0, 1, 2.
What is this
Minus
number?
2 only.
This is also minus 2, right? So you can see here that either you represent it as 1 0. Now this can't be number in a signed number system, because that in this case this would be taken as a sign bit over here. So if you are taking it in 2 bits, then this is the sign bit over here, so it's again going to be minus 2 in this case. But if you want to store the same number in a bigger space, you just extend its sign, right? So this is actually minus 4 plus 2. This is actually minus 8 plus 4 plus 2. This is actually minus 16 plus 8 plus 4 plus 2. So you can see here that if I extend a sign to it, it's twice the size of this previous weight. So if I don't do that, that's also the same thing. So actually this is the same as this, right? And these two are the same as this, right? So when you're talking about storing a number, a negative number over here, so if you want to store it in six bits, you just extend that sign and that becomes a 1 over here. So we have to add these two together, and we are going to add that in the next step and then shift it to the right to get this number here. And then again do the same thing. It's second bit is 1, add 10110, 1 to 1 more to that. Now the point I was telling you was, let's try to add these two together. So 1 plus 0 is 1, 1 plus 1 is 0, 1 carry, and 1 plus 1 is 0, 1 carry, 1 plus 1 is 0 and 1 carry, and 1 plus 1 is going to be 1 and 1, and 1 plus 1 is going to be 1 and another carry. So that carry is discarded. So now you're left with this number. And the reason for taking that extra bit was that you know what should be shifted into that 5-bit system here, 5 bits that you are concerned with. So this one is going to make it simple for you to know what should be shifted into it, because I'm going to give an exercise where this is going to be a problem if you don't have these extra bits over here. Okay, the same thing is over here. You can go through that yourself. We don't have much time, so I'm going to leave that as an exercise for you to go through that, and you can check it. What is the result that you obtained? So what is this number that we have here? What is our multiplicand? 10110 in a sign in 2's complement number system, and in sign number system, 2's complement number system. What is this number?
Uh, Sir, minus 10?
Minus 10. So it's minus 16 plus 10. By minus 16 plus 6. So minus
Yes.
16 plus 6 is minus 10. And what is the second number? Is anyone
11?
else?
Isn't it?
11, right? So, we need to multiply minus 10 with 11, right? Minus 10 with 11 would give us minus 110, right? So we are
Yes,
going
sir.
to see whether we have obtained the right answer over here. Now, if there are multiple ones in the beginning, now these numbers were of 5 bits, and so our result should come in 10 bits. That's one thing that we know. Okay, so this is the 10-bit result over here. So if you have got extended ones in the beginning, you can come to the last one and give that as a negative weight. This is what we have discussed right now.
Yes, sir.
So uh, 2 is power 0, 1, 2, 3, 4. There is a voice coming. Miss Senior, please can you
Yes, sir.
mute yourself? Yeah, thank you. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 7. So 2 is power 7. 2 is power 7 is actually 128, right? So we could have gone for 2 is power 8 and 2 is power 9, but 2 is power 7 and they are extended ones. So we can have this as a negative weight. So that could be minus 128. So minus 128 at this point, and we are adding 32 to it, sorry, 16 to it. 16 plus 2, that is 18. So minus 128 plus 18. So minus 128 plus 18 is obviously minus 110, right? So we got our answer minus 110. So here we have discussed is with the minus 512 plus 256, but you can see that if you are going to do addition between these two, you are going to get minus 256, and if you are going to do with these two, you are going to get minus 128. So we started with minus 128, right? Okay, so this is simple if your multiplier is positive. But now let's come to the next case. If our multiplier is negative. Now, if our multiplier is negative, this means that our multiplier will have a 1 at this position. And a 1 at this position is actually a negative weight. And when you have a negative weight over here, the only change you need is the last step. So instead of having an addition over here, we need a subtraction over here. Okay, so instead of having, so that's the only thing that you have to do. So in the last step, the sign bit, so you are going to subtract rather than add. So the same algorithm can work in this case if you have a right shift algorithm. So you can go through that yourself and you can see whether you have obtained the right answer or not, right? So one way to do that is, so I hope every one of you have some pencil and paper with you. Do you have that?
Yes,
Because
sir.
Sir. Yes, sir.
okay, good.
Yes, sir.
Because now I would like you to have one question here. So I would like you to solve this. So what you can do is you can copy a and x. Just copy a and x. So a is 0, 1, 0, 1, 1, which is a positive number. X is 1, 1, 0, 1, 1, which is a negative number, right? So a is 1, 0, 1, 1, which is 11, and x is, what is x? So we have a minus 8 over here because there are 2 ones over here. So we can take this as a negative 8. Minus 8 plus 3, that would be minus 5. So we are actually multiplying minus 5 with 11. So you know the answer should be minus 55. Okay, so the good thing about these problems is you know the answer, and you could try to find out how to get that answer, the same answer. Okay, so let's once you have copied that, so I can come back to my previous slide where you can look at the steps. I need you to do this thing yourself. I was hoping to start boost algorithm, but let's see if we have got time or not. Okay, so so I hope everyone you have copied. So I'm going to come to the next slide, so to the previous one where the steps were mentioned. Okay, right. So I'm going to open this slide for you. You can change the a and x, but this is just telling you the steps that are required over here. So the last step has to be a subtraction step over here because the multiplier was a negative number. So try to do that yourself. Try to do that yourself and see whether you obtain the right answer. and you can show me your results as well. Okay. I'll do things. I'll do something better than that. So what I can do is I give this as an exercise to you. You have to solve it by pencil or pen, whatever, not on computer, right? Solve it by your own handwriting, and I'll give you the slide. I'll just upload that today, inshallah, by 9 o'clock. And then what you have to do is do this yourself. Okay. So this slide has the answer. I'm going to take it out and I'm going to quickly go through that. You have to do that yourself, right? So you have to do that yourself, and I'll give you a short assignment, and you have to submit that by tomorrow. Okay. So I'll give you, or maybe let's take one more day, so you can submit it by Saturday. Okay. So you can submit it by Saturday. It's a small exercise, just go through that. So I'm going to come to the next topic, so I'm going to skip that thing together. Okay. So this is then the hardware multiplier that we have discussed. So that this is going to take a 2's complement hardware multiplier that we have discussed. Now you can see from a unsigned number system, it's a little complicated, because instead of having a 0 and a 1 over here, what we are having is uh, the multiplicand and the negative of the multiplicand, right? Or the complement of the multiplicand. Now this complement here is actually needed only in the last step, where you are going to do the subtraction, right? So this is this multiplier is going to have a 0. The carry in is always going to have a 0, where you're always going to add, except in the last cycle where it's going to be 1. So this is by design that you are going to make it in such a way that in the last cycle you're going to give a 1 to this adder. A carry in of 1 means that this adder converts to a subtractor when you have a multiplicand in its complementary form, right? So you know that this principle, how to convert an adder into a multiplier. So you have to do a one's complement of this. There's this one's complement is happening over here. The multiplicand is going through a complementary option here, and this is going to be 1, which is going to select this input only in the last cycle, and then the remaining is almost the same as we have discussed earlier. Okay, so let's move forward. Now let's come to the better way to do sign multiplication. So in the last scheme, the right shift algorithm that we saw, it was good, but it got a little complicated, because sometimes we were doing addition, sometimes we were doing subtraction. So that got a little complicated. So we have to take care of those last steps where we have to do. So Boost algorithm is basically designed only for signed number systems. So you by design is considering all these numbers to be happening, having both positive and negative numbers. Okay, so what is Boost algorithm? Now, when we come to a number like, okay, so I'm going to initially start with an example of decimal number systems. So if I ask you to multiply 45 with 99 or 98. So if I ask you to multiply 45 with 99, what would be your result?
4455.
Okay, so how did you do that? It was simple, 45 by 99, like this. So you are going to do it like this. That could be done. That's what a normal procedure is. Or you can do it another way. So 99 is actually 90 plus 9, and you are multiplying with 9 and another 9, and then you're going to add it. What you can do is think about 99 as 100 minus 1, right? And when you think it in this way, this 100 is a good thing to have, because this 100 means you simply have to do nothing but shift it twice. So that becomes 4500 minus that 1 here is going to be 45, right? So instead of having two different addition operations, you have converted into a single addition operation or subtraction operation, in other words. So two operation converts to one operation just if you are doing a number like this, but this is only for special numbers which are closer to that basis here. Okay, 98 could be done in the same way as well. So 98 would be 900 minus 2. That's also simple, right? So what I'm trying to say is, if you have got a binary number 101 or 1101, something like that, uh, you go for these sequences of 1, and then you convert these sequences in a different way. So you do you have a 1 over here, some zeros over here, and a 1 over here. So you convert this thing into a different number. So 111 is actually this number here, 8 minus 1. Okay, so instead of having 3 additions, you will be doing 1 addition and 1 subtraction. So this makes the number of operations less than the previous case. This is only going to have benefits if you have got sequence of ones. So if you have got in a number some ones like this, so actually this number is 31, but you can convert it into 32 minus 1. So instead of having 5 additions, you are going to do just 1 addition and 1 subtraction, and then you're going to get your result. So the same thing happens in Booth's algorithm. So the same thing happens in Booth's algorithm, that we are looking for sequences of these numbers, and for that we need to look at 2 bits at a time, and then we are going to recode that into another number system. So this number system has got 3 values, 0, 1, and minus 1. So it's not a binary system, it's a different symbolic number system. It has got 3 numbers, 0, 1, and minus 1. 0 is for doing nothing, 1 is for addition, and minus 1 is for subtraction, right? So let's try to do it for a number like this. So okay, do I have this as a single one? Okay, I have the answer with me as well. Okay, so let's try to do the same. So this is our operand 1001 1101 10101110. So this is our operand, and we need to decode it looking at this table. Okay, so we look at 2 bits at one time and convert those 2 bits into a single symbol having 0, 1, or minus 1. So now, since this is our first bit over here 0, and there is no bit over here, so we are going to take 1 extra bit to see what should be. That extra bit is only going to be considered for this LSB, and it's always going to be considered as 0. So 0, 0 in our table is 0, so we are going to put a 0 over here. The next time we are going to have between 1, 0, right? So the first time we did it for 0 and we considered a 0 over here. The next time we are going to do it for 1, 0, and 1, 0 means minus 1, so we are going to put minus 1. The next time we are going to do it for 1, 1, and that's 0. The next time we are going to do it for 1, 1, and that's 0. The next time we are going to do it for 0, 1, and that's 1. Next time we are going to do it for 1, 0, and that's minus 1. And likewise we can do it for, so we are going to look at 2 bits, except for the first time we are going to take 1 more extra bit ourselves. So likewise we are going to do it. So these 2 over here, these 2 over here, 1, 0 is minus 1, 1, 1 is 0, 0, 1 is 1, 1, 0 is minus 1, and 1, 1 is 0, and 1, 1 is 0, and 0, 1 is 1, and 0, 0 is 0, and in the end we have 1, 0, which is minus 1. So this is a recorded form. Now in this example, it's not going to be evident what's the advantage. So because if you can see, we have what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones, and we converted into recorded form, which has got So we are going to look at ones or minus ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's not much of an advantage. From 10 operations, we converted it into 9 operations. But on average, you're going to see whenever you're going to recode in Booth's algorithm, things get the operations get smaller. The operation sizes get not the sizes. The number of operations gets fewer. Okay, so how can we help? How can we take help from Booth's algorithm? So as I mentioned that what we are doing is reducing number of operations. Here, each one means that we are going to add, and each minus one means we are going to subtract. So let's take an example, and this would be this is going to be our last example. So I'm going to stop over here. So I'm going to take this example here. Okay, so in this case, we have again the multiplicand and the multiplier. So we are going to take two numbers over here. So you know what this number is. We have got minus 16 plus 6, which is minus 10, and minus 16 plus 5, which is minus 11. So again, we are multiplying minus 10 with minus 11. So the result should be 110. Okay, so that should be a positive number. So first, let's try to recode our multiplier in its boost recorded form. Now this is a special multiplier. If you have got a sequence of ones and zeros, that's the one which is going to give you always a 1 and a 0, because the advantages that we are having are on whenever we have the same zeros or ones, then it's going to be a no operation. Otherwise, if you're changing the bits, it's going to be a different operation, right? That was discussed in the last slide, where I've written the reasons over here. So okay, so again we are going to start with the first product as 0, right? So our first bit, now we are going to look at the boost recorded form. So if it's minus 1, you're going to do subtraction, right? Which is addition of the 2's complement form of A, right? So this is actually minus 10. The 2's complement form is 10, or you can compute it separately. So if it's minus 1, you are going to add 0, 1, 0, 1, 0. If it's 1, you're going to add 1, 0, 1, 1, 0. And again, take one extra bit to look for the sign, and then you're going to get the right answer. And this is much simpler than the right shift algorithm, remember. Okay, so let's start. So the first bit is minus 1. So we are having 0, 1, 0, 1, 0. We add these two, shift right. Then our next bit is 1. We are going to add 1, 0, 1, 1, 0. So we are going to add 1, 1, 0. So you get 1, 1, 1 plus 1, 0, 1, 1, and 1 over here, right? And this is the, again, extended bit. If you don't want to write this same thing that is coming over here, both at these two positions once you are going to shift it to the right. Okay, next is minus 1. Add the 2's complement of that, 1, 0, 1, 0, 1, 0, 1, 0, and then do the shifting. And then the next one is 1. Add 1, 0, 1, 1, 0 to it, and then you are going to get 1, 1 plus 1, 0, 1, 0, 1, 1, and you have a 1 over here, and the same bit is going to be written over here and here. So this is something which is an extended form of this. If you can do a proper right shift yourself, arithmetic right shift, you don't need to write this one. Okay, so this is then the last step, minus 1. I add the 2's complement of the multiplicand, which is 10, 0, 1, 0, 1, 0, and then you are going to get this number, and finally a last shift, which is going to give this number. And this is again the same thing that we did in the first example. So it's again 110, right? So this is a much simpler way to multiply two numbers here. Here you can see we are doing multiplication and additions at different steps, looking at the boost recorded digits or symbols. Okay, so I'm going to stop over here. Our next, okay, yes, we are going to continue with high-speed multiplication in our next class. So I'm going to post this slides on the group on the classroom, and also your assignment. So you have to do that by Saturday. Okay, it's a simple thing. Do it by hand, and just post me uh, just give me that picture or don't try to do it on computer because it's good, but again, by hand is much better if we are taking a virtual class, right? So I'm going to stop over here. Right, are there any questions here?
Sir, I asked you for the recorded lecture since I missed the last one, and they have not been uploaded yet. Please, can you
uh,
upload any one of them so that I can go through the Amdel's law? I didn't attend the class first one.
have you checked your drive?
Yes, sir, I have checked my drive.
Were you not there in the first lecture?
Yes, I was absent, sir, due to there were some issues
No,
in
no,
my.
no. You were not added. You were not added to the classroom. I think you were added to the classroom.
I was in the classroom, but I didn't attend the class because
It doesn't
cybersecurity.
matter. It doesn't matter if you attend the class or not. If you're added, every student is going to get these recordings.
Okay, okay. Are they the recordings are there in the drive?
Okay.
Because
Yeah, yeah. Maybe that's the case because the
Sir, hello. Me also, I can't find.
okay, maybe so those who are absent, it actually needs a consent from the students, but since this is a university policy, so everyone has to give the consent. All these lectures have to be recorded. So I'll give you the link. If you don't have that, I'll give you the link.
okay, thank
Sir,
you.
sir, okay, me also, I can't find anything in my drive,
Uh,
Google Drive.
yeah, but I have checked. You are you checking your drive of the cloud ID?
Yes, Google Drive with this ID. No, I haven't nothing. It's
Oh,
empty.
okay, I'll give you the link. I'll give you the link, but I have seen that in my drive, so it's there. I'll give you a link
Uh,
and share the link on the classroom.
okay, inshallah.
Okay,
Thank you, sir.
thank you, thank you.
Also, sir, I send you email about this issue, but is your email that you send notification?
Which email address were you using? The same email address?
I don't know your email address, but I make reply for your email that you send the notification in our Gmail in our ID.
You told me about this issue of not getting the recordings.
Yes.
Okay, I'll check that. I'll check that.
Thank you, sir.
Maybe I have missed that because this same ID. I'm teaching a course at undergraduate level, and then there are 150 students, and whenever
Okay,
something is
thank you.
commented, so I just get a lot of emails and on that ID, right? So maybe I've missed that.
Thank you, sir.
Okay, thank you. So take care, all of you. Allah Hafiz.
Officer.
Yeah.
Allah Hafiz.
Allah Hafiz, sir.